You can see my mouse, right? This, by the way.
Yes.
Yeah, okay.
So our next speaker is Rob Klabbers from Nordita. Please, Rob.
Yeah, thank you very much. So I want to talk about a work that I published this year with Jules Lamers on the Inozemtsev elliptic spin chain, which is in principle just all the spin chain of electrons to spin 1/2 particles on a circle. The main difference with most of the spin chains you guys know is that actually in this particular case, every pair of particles interacts. This interaction is very simple. It's simply just a permutation operator minus the identity. But the difference is that now this spin operator gets weighted by an elliptic function where the argument is just the distance between the two particles. This elliptic function you can think of as a doubly periodic version of a second order pole, where the real period is related to the length of the spin chain, and the imaginary period, which I call omega, I parameterize by a variable called kappa. And I do it in such a way that the real and the complex periods are really orthogonal, so that I have a rectangular lattice. Now, Inozemtsev came up with this model in 1989, and he realized that it must be a very nice model because it's SL2 invariant, it's translationally invariant, and periodic. So there must be lots of interesting things you can do with it. And let me at least say that even though there's an elliptic function here, you shouldn't think of this as some kind of elliptic XYZ-like model. It really is isotropic. So it has really, it's orthogonal to what you usually think of when you think of elliptic in the spin chain world. So Inozemtsev managed to solve this in a series of papers in the 90s, as you can see. And of course, the question is, okay, if you can solve this exactly, is it also quantum integrable? And the answer to this question is still not really understood. So there's a whole range of different literature that goes from integrability to n=4 with a famous paper by Serban and Staudacher, to more modern work on thermodynamics and Calogier-Sutton Moser systems that shows that this spin chain has many different types of applications. And thus should be interesting enough to study, of course. Now, my personal goal is to understand exactly what the role is of the spin chain in this particular diagram. So what I plotted here is different sets of potentials. Here on the top, I have the potential for the elliptic model. So this is just one of the different choices for V I can make for this Hamiltonian. And then each of these choices in this diagram gives me an exactly solvable system. So this is Inozemtsev and its infinite length degeneration. Here I have the Heisenberg model, which of course all of us love and know very well. And on this side, I have the Halding-Shastry spin chain. So Inozemtsev really goes from a model we all know very well, all the way to a model that at least is also very interesting. It's also quantum integrable. It's a very simple model for the fractional quantum Hall effect. And it has a Yangian invariance. So its multiplets are extremely degenerate. So this is a very interesting thing. And I would like to understand better how this works. And in particular, if Inozemtsev is integrable, and if so, what kind, and what can we do with this? And our recent work is a way to answer this question. Basically, it produces a new parametrization of the solution to the spectral problem in the form of some coordinate Bethe ansatz that yields Bethe equations that previously did not exist. It allows you to take limits of all the quantities in the spin chain. It gives you additive energies, at least almost additive as you could possibly wish for. I will show you in a second what I mean. And it gives you rational equations for the spectrum, in the same that you can get rational equations for the Heisenberg spectrum in terms of rapidities. So all in all, this gives you extremely good control over the spectrum and opens up all kinds of different new directions. Now, how does this work? The coordinate Bethe ansatz we have all studied just asks you to solve the spectral problem in the coordinate basis, where the spins up are counted by a vector n, and I have to give you an ansatz for the wave function component psi. For the Heisenberg model, we have just the sum over plane waves where we have to find these coefficients, and imposing periodicity gives you the Bethe equations. Now, Inozemtsev already said, okay, what if I just allow these coefficients to be dependent on positions as well? Can I solve it then? And the answer was yes, just not super conveniently. So our version of this is very similar to this. We just shift the plane waves by a bit, and we give a very particular interpretation to these coefficients that turns out to be very convenient. So let's study this in a little bit more detail. In particular, these P's are now actually quasi-momentum and are quantized by periodicity through a set of Bethe equations. So this is the solution, or at least this is the ansatz, I should say. And I'll turn this into a solution by correctly identifying all the components. So this function psi tilde here is actually a solution to a different spectral problem. It's namely an eigenfunction of the elliptic Caligero-Sutherland-Moser Hamiltonian, which is a Schrödinger operator with an elliptic potential as well. And the energy is very simple of that particular spectral problem. It's just the kinetic part plus the potential part u tilde. And eigenfunctions psi tilde depend on two sets of parameters, p tilde, which are just quasi-momenta, and then some set of variables phi, which you can think of as packages of scattering phases. Now, these have to satisfy some constraints, and then you have a solution to this problem. And to turn this ansatz into a solution to the spin chain, you have to ask for a little bit more. First of all, you have to get actual Bethe ansatz equations, as you wish for a normal spin chain, which relates to momenta, the quasi-momenta, and phi. Moreover, you have to also identify the quasi-momenta of the continuous model of the Schrödinger operator with those of the spin chain. And now if I package everything together, I can say that I found an eigenfunction, given that these constraints hold, and the energy is extremely simple. It's just a sum over the dispersion evaluated at quasi-momenta, exactly as you would wish. And there's an extra bit, which basically just depends on what type of solution you choose for the elliptic Caligero-Sutherland-Moser Hamiltonian. So it's very simple. So in principle, if I manage to find a solution where u tilde equals 0, I would get fully additive solutions. Now this might of course be too much to ask for, but at least it's as close to additivity as you could wish to go. Now, this solution is very nice. As it turns out, if you unpackage these packages phi into individual scattering phases, it turns out that that the constraints are actually elliptic functions in each of the t's, each of these scattering phases. This means through elliptic function theory that they can actually be written as rational functions of y plus p of t and y plus p tilde of t. And since I can actually say the same about the energies, which are elliptic on shell, so up to a correction proportional to the constraints, this means I can write everything in terms of these new functions, p of t and p tilde of t. This turns the entire spectral problem into a rational problem. And of course, this is very nice. So in particular, for two particles, the Bethe ansatz equations are just this simple rational function, or this simple rational equation. I have to just find values x hat of t, given the rest of these numerical values. It's very easy. And now I can basically do whatever I want. For example, I can find the spectrum. It's for 6 particles, although I could have also chosen more particles, but this is just easier to see. And I can really trace multiplets of the Heisenberg system, which are labeled by the Bethe counting numbers, all the way to the eigenfunctions, to the multiplets labeled by motifs in the Haldane-Shastry spin chain, where these multiplets are Yangian highest weight states. And this is very interesting. And it has led to some new observations. One thing we found out is that for Heisenberg, the 3 different types of states can actually be put in one-to-one correspondence with states from Haldane-Shastry. So the scattering states of Heisenberg are actually Yangian highest weight states once I move them through. And SL2 descendants are still descendants for Haldane-Shastry, which, because of the presence of a Yangian, I call them non-affine descendants. So these are descendants which are basically like SL2 descendants. Whereas the bound states of Heisenberg have to disappear for Haldane-Shastry, and they turn into affine descendants. So you get them from Yangian's highest weight states by acting with generators of the Yangian that are not in SL2. And we can actually prove this at 2 particles, and we see that it almost certainly has to hold also for higher m, where m is the particle number. And this really begs the question how the 2 Yangians of Heisenberg and Haldane-Shastry are actually related, which is a very interesting question to ask, in my opinion. And a second big observation we found is that the spectrum of Inozemtsev has 4 different kinds of bound states that actually generalize the concept of critical length that you have for Heisenberg. And since I don't have that much time today, I won't be able to go into that, but my paper with Jules talks about it in length. So all in all, basically in this new parametrization, the elliptic spin chain is completely solved. It's very easy. The energies are almost additive. The spectral problem is completely rational. You can do any limit you want. It's very, very straightforward. Now there's other stuff that I didn't even have time for. There's an S matrix, which you can define, which is a generalization of an S matrix to the finite length setting for long range spin chains. And you can ask the question how Heisenberg Bethe integers are related to Haldane-Shastry motifs exactly, how this correspondence works exactly. There's all kinds of complex bound state structures to analyze, which is also interesting. And finally, the trick that Inozemtsev introduced, we perfected to compute different types of elliptic sums. And of course, this is just a technical tool that is interesting to see. And in the future, we'd like to study the connection between these 2 Yangians. This, of course, is a very deep question of integrability. And to study the completeness problem beyond the two particle sector, for which we can already do it and prove it completely. And finally, Basically, the holy grail for me in this field has been for years that what I actually want is to find the anisotropic generalization of the spin chain, which would be to really turn this diagram from my second slide into a three-dimensional picture and get something for these different question marks. Thank you.
Thanks a lot, Rob. Please unmute yourself and let's thank the speaker. And so we have time for questions.
So, okay, I could ask. So what is actually the Bethe ansatz at the end? Because I don't know, I didn't see it. And what was it found before, or so your point is to construct the wave function mostly? Or?
Yeah, so this is the Bethe ansatz.
No,
the
what
question
I mean
is still
like Bethe ansatz for beta roots type of thing.
So your question is, what is the form of these equations?
Oh, I'm not in the ball in this notation. I don't recognize the minimum, but I mean like
Well, what you're asking for is a set of equations that then ultimately constrains the roots.
Yeah, which determine rapidity.
Yeah, so these are still, well, this is, one example would be this. This is a set of a Bethe equation, and you have to solve it, and this gives you Bethe roots. I just wouldn't call them, if you say Bethe roots, you have a very particular thing in mind. And of course, you have to question whether all of those, let's say, stereotypes are still holding for this elliptic generalization.
But the question, what is the then procedure of finding the spectrum? What one should do?
To solve for the spectrum, you solve this equation for x of t.
Yeah, but that's for some for two particles, right?
Yes.
And for more particles?
For more particles, this will look a lot more complicated because you have more different types of x's, and you will get coupled sets of equations. I don't have them on the slides, but they're a lot more complicated.
Mm-hmm. But they are not for in general. Yeah, sorry, Volodya.
So we don't have the rational form of them in general, because that is actually a very hard question to ask. In transcendental form, they're not that hard to write down, but it would still require a lot of notation.
Volodya?
In the weights of this model, you use the elliptic function with modular parameter 1. What is the reason for it? The integrability breaks down if you choose any other tau.
So tau is not exactly 1, actually. Tau.
What you
so normally
showed is
tau is
it's rational, yes.
I guess it depends a bit on your definition, but I
So
guess tau is normally omega 2 divided by omega 1. And kappa is just rational. So kappa is just some real number. So you get I pi divided by kappa times L. And this can be any number.
But not continuous.
No, it can be any number, any imaginary number. Just it has to have positive imaginary number. Positive imaginary part.
I see. Okay.
Hey, can I ask another question? Could you speculate on how the Yangians are all going to fit together? I mean, I know you don't have the result yet, but is there any preliminary indication?
Honestly, it's a very hard question. The only answer that I would give is that so we don't understand really when we get bound states for the Heisenberg model. Like we can't really in advance say when we write down the equation which of the solutions are going to be bound states. And somehow it seems like there must be some extra structure that we haven't seen, that you should be able to identify this in advance. And this then you should be able to relate, because in principle, the origin of these two Yangians is very different. One really directly axial to Hamiltonian, and the other one is part of the Bethe algebra. So honestly, I wish I could say something more. Even my speculations, I feel, are slightly foolish.
No, this always struck me as an unsolvable problem. So you at least have some progress on how one might attack it. So this is good.
Other question? One more question, maybe?
Hi, Rob. Do you have like a lax formalism for this R matrices for all of your chain?
Which R matrices are you?
I mean, like, in the context of algebraic Bethe ansatz, not coordinate.
Yeah, this is a great question. So there is no R matrix. There is no algebraic Bethe ansatz for this model. You could say there should be some. So you could basically say that if I'm very lazy, I could say this this spin operator is a very trivial representation of an R matrix. But there's no way to do algebraic Bethe ansatz yet. This is, of course, if we could, there would be integrability. You would solve a major issue.
But you cannot guess, like, normally you could take R matrix and take a derivative and get a local Hamiltonian.
So you cannot. We have a little bit about this in my paper. You can ask me later. I'll tell you where to find it.
Okay, thank you.
Just to remind, we will have